8 in the last class we started carbohydrate and we studied different structure of carbohydrate. Okay, so today let's start with D and L sugar. So D means dexa and dexo, and L means levo. So for a sugar down in the feature projection with the most oxidized carbon atom at the top. This is the most oxidized carbon atom at the top, and these are aldones, where the hydroxyl group on the bottom chiral center point to the right side is called D sugar, and if the hydroxyl group on the bottom chiral sugar center to the left is called L sugar. So what I said, so for a sugar done in a Fischer projection, so this is D glucose and L glucose. These two are these two are mirror image because of their enantiomers, so those two are mirror image. But in the mirror image, if the hydroxyl group on the bottom chiral center, this is the bottom chiral center, this is not chiral center, so this is the bottom chiral center. If the hydroxyl group on the bottom chiral center is in the right side, this is called dexa or D-glucose. In the left side, it is called levo or L-glucose. So D and L designations of sugar are based on the position of hydroxyl group on the chiral carbon first from the carbonyl group in the feature projections of the molecule. Okay, so let's study alpha and beta glucose. So glucose exists in different forms called structural isomers, and the two common isomers are alpha glucose and beta glucose. The only difference between these two isomers is the position of hydrogen and hydroxyl group attached in chiral or carbon 1. In alpha glucose, the hydroxyl group in carbon 1 is below, and in beta glucose, the hydroxyl group in carbon 1 is above the carbon. And only difference and this minor structural difference has a major effect on the biological roles of alpha and beta glucose. Look at here in the table, these differences are mentioned. Like the alpha glucose are less stable, but beta glucose are more stable. So alpha glucose are highly energetic, beta glucose is lesser energetic, and melting point is lower and melting point is higher. And enzymatic action, they are easily broken down by the enzyme, but beta glucose resistant against enzymatic actions. And 2 alpha glucose gives maltose, 2 beta glucose gives cellobiose. Okay, so this is the polymerization starch. So starch is made up to alpha glucose and cellulose is made up to beta glucose. Mutant rotation. The alpha and beta anomers of D-glucose interconvert in aqueous solution by a process called mutant rotation. Thus, a solution of alpha D-glucose and beta D-glucose eventually form an identical equilibrium mixture having identical optical properties. This mixture consists of about 1/3 of alpha D-glucose, 2/3 of beta D-glucose, and very small amount of linear and 5-member ring. So what I said, the alpha anomers and beta anomers of D-glucose interconvert in aqueous solution by a process called mutant rotation. Okay, so pyranose and furanose. This is the pyranose and this is the furanose. That means 6-member ring is called pyranose and 5-member ring is called furanose. So in pyranose, the carbon number containing in the ring is 1, 2, 3, 4, 5, and in furanose the number of carbon inside the ring is 4. Okay, so particularly these are important hexose and pentose. So this is hexose and this is pentose. And here you can see the examples of pyranose and furanose. So those are isomers. So alpha glucopyranose, beta alpha fructopyranose, beta glucopyranose, beta fructopyranose, and the common ring structure is here, pyran and furan. Okay, So the six-membered Pyranose ring is not planar as Howard perspective suggests, but tends to assume either in two-chair form conformation, and the specific three-dimensional conformation of the monosaccharide units are important in determining the biological properties and functions of some polysaccharide. Let's study the formation of disaccharide bond. Disaccharide contains a glycosidic bond. So to define glycosidic bonds, when the hydroxyl group of one sugar react with the hydroxyl group of anomeric carbon of another sugar is when the hydroxyl group of one sugar react with hydroxyl group of anomeric carbon of one sugar releases one molecule of water and making a bond. This is called glycosidic bond. So the glycosidic bonds are two types. One is alpha glycosidic bond or beta glycosidic bond. More there each class have two more different sites like alpha 1,4, alpha 1,6, beta 1,4, beta 1,6. Okay, so if the anomeric carbon containing sugar is in alpha form, the bond will form is alpha. If the anomeric carbon in the beta form, if the anomeric carbon of the sugar is in the beta form, then the bond will form beta. That means the sugar that involves in bond formation, the sugar that is involved in bond formation, if it's alpha carbon involved in bond formation, so the position of hydroxyl group in the alpha carbon will determine the bond. Okay, look at here, this is alpha glucose and this is beta glucose. So we cannot determine the bond name based on this one. We can determine the bond based on this one because this is the sugar which alpha carbon has been involved in the bond formation, but here the alpha carbon is not involved in the bond formation. Okay, so how do alpha and beta glycosidic bonds differ and how can this affect digestion? So alpha differs from beta glycosidic bond only in the angle of formation between two sugar, angle of formation. So alpha glycosidic linkase is below the plane of the ring and beta glycosidic linkase are above. So human who lack the enzyme need to cleave the beta glycosidic linkase suffering from lactose intolerance. So here you can see the anomeric carbon of this sugar involved in the bond formation. So this is alpha. The anomeric carbon involved in the bond formation is in beta. So this is called beta. So here are some examples, important examples like lactose. This is in beta form because this sugar, the anomeric carbon is in beta form. Okay. So here are some examples you can study or practice. Okay, so most carbohydrate found in the nature occurs as polysaccharide, and polysaccharides are also known as glycan. And polysaccharides differ from each other in the identity of their recurring monosaccharide units, in the length of their chain, in the type of bonds linking the units, and in the degree of branching. So that's all from this lecture. See you in the next lecture.